Well, hello, pre-calculus students and seekers of general truths. In this video, we continue our work on finance mathematics, and we look at a somewhat complicated example. So let's just see what the problem is here. All right. So a mortgage or a home loan of $80,000 for 30 years at 12%. By the way, 12% is huge. This is not practical. You should never take that deal. But let's pretend that you were silly and you did take that deal at 12%. And it requires payments of $822.89. I've added this work here in blue just to show you how that 822.89 was calculated, right? So just a quick review. On the left side is how much we would owe the bank. The bank gives us $80,000 once, and that amount gets compounded at 12% monthly, so 12 times per year, for 30 years. 12 times per year, so 360 times over the course of 30 years. Right? And whatever that number is, we set that equal to the right side of the equation here, which is the annuity formula, how much money we're going to put in every month. And when we solve that out, we get $822.89. Okay, so now, that's just a quick review. That's not really the question that we're asked to deal with here, but hopefully it serves as a reminder for us to set up some of these problems. Okay, so A, if we decide to pay $1,000 per month, how long will it take to completely pay the loan? Okay, so this is a good question to work on. So we can kind of look at this work up here, right, and tweak it a little bit. So if we're paying $1,000 a month, then this time we do know big R. All right, so we do know, for example, that whatever it is that we're paying, however long it takes us to pay, we're going to pay $1,000, and the rest of the equation sets up as follows. 1 plus, the rate is still the same. It's still 12%, right, compounded monthly. Now, what's going to change here is the 360. Because we're paying more money per month, it's going to take less than 30 years to pay off the loan, right? If we were to pay $1,000 a month for 30 years at these rates, we would definitely exceed this number. So we would pay too much. Okay. So what's an important factor in this is that the time is going to change. It's still 12 months per year, but we don't quite know how many years. So it's going to be 12 to the T. Okay. And the denominator, or the bottom part of this equation, is still relatively the same. It's still 1 minus 1 plus 0.12 over 12, okay, in the denominator. And that is going to be equal to the future value of the loan. Right? Now, what people often make a mistake is that they say $80,000. Okay, this is just wrong because it doesn't factor in the interest that the bank is making us pay. Okay, so the bank still charges us interest. Okay, so it's still 12% compounded 12 times per year. And some people will also put 360 here. And again, this is also wrong because if we were to pay $1,000 per month, it's not going to take us 12 years to pay off this amount. It's not going to take us 12 times 30, right? Sorry, 30 years. It's not going to take us 30 years to pay off this amount. It's going to take us a little bit less time. Right? However much time that is, it's going to be 12 times T, where T represents the number of years. So one point of emphasis I want to make here is that the amount of time for the annuity and the amount of time for the future value of the loan has to be exactly the same. Okay, so same time period, right, for the loan and for the annuity or the payment plan. It is incorrect and really grossly unfair if there was an imbalance in the time here. If you borrowed something for a basis of 30, if you had to pay interest for 30 years, but it took you less than 30 years to pay off the loan, okay, that's actually probably illegal. Okay? And it would also be impractical, and no bank would allow it, that if you were to take 30 years to pay for something, but the interest that the bank is charging you only accumulates for less than amount of time. So the amount of time for the annuity and the amount of time for the compounded interest has to be identical. Okay? And now we're left with this very, very complex and messy equation that we're going to have to solve for. Okay? So what I'm going to do, or the strategy that I'm going to employ, is just to simplify this equation by means of a substitution. All right, so notice here that we have kind of this, not kind of, we have the same expression on both sides, 1 plus 0.12 over 12 to the 12t, 1 plus 0.12 over 12 to the 12t. So I'm going to replace that with a different variable just to make the equation a little bit more manageable. So I'm going to call that w. All right, and we're going to solve for w first and then solve for t later. Okay, so my goal now is to solve for w. And then when I'm done with that, I'm going to use my value of w to solve for t. Okay? So let's rewrite this equation here. So if we rewrite this equation, this will be 1,000 times 1 minus w over, and I'm going to simplify this as well. All of this in the denominator turns out to be negative 0.01. Okay, so 1 plus 0.12 over 12, and then 1 minus that is just going to be negative negative 0.01. On the right side of the equation, I'm going to have 80,000 w. Okay, so solve for w first, and then we can solve for t later. Okay, so some more cleaning up to do here. Multiply both sides by negative 0.01. And that will give me negative 800w, okay, instead of 80,000. Then divide both sides by 1,000. So that's give me 1 minus w equals negative 0.8w. So again, dividing by both sides by 1,000 gives me this expression. Then I'm going to rearrange. I'm going to add w to both sides. So negative 0.8w plus w will give me positive 0.2w. Okay, so I'm adding 1w to both sides. Then I'm going to divide both sides by 0.2. So that gives me that w is equal to 5. And that's great, but we're not quite done, right? So we've solved for w, check. Now our goal is actually to solve for t. That's the real work that we have to do here. So now we got to solve for t. But it's not too bad because we already know a relation between w and t. We know that w, which is 5, is equal to 1 plus 0.12 over 12 raised to the 12t. Okay. I'm going to simplify the stuff in the parentheses. It's just 1.01 to the 12t. Okay. And again, at this stage, you could do a lot of different things. You can convert this into log form, log base 1.01. I like to just take the natural log of both sides. So the natural log of 5 equals the natural log of 1.01 to the 12t. Using the power rule of logarithms. So let's continue this over here. Using the power rule of logarithms, the left side is still natural log of 5, and the right side is 12t times the natural log of 1.01. Divide the two, natural log of 5 over the natural log of 1.01 gives me 12t. And then one last step, multiply both sides by 1/12, and that'll give me the value of t. Okay, so natural log of 5, natural log of 1.01 will give me the value of t. And so the approximate final answer is 13.5 years. Okay. So that's approximately what t is equal to. And so we can think of this as 13 years and 6 months. Okay. All right, so 13 years and 6 months is 162 months, however we want to put it. Okay, 162 months, approximately. So let's go back up here and recap our work a little bit and get a sense of, let me put in a big box here as my final answer. But let's recap our work here a little bit. Given the loan that we've taken out, if we were to pay $822.89 per month, it would take us 30 years to pay it off. But if we were to pay $1,000 per month, it would take us 13 and a half years to pay it off. So we're saving a lot of time of owing the bank money. Okay? Now for part B, let's just see what the difference is in the amount of money that it would take us. Okay? So in the first way, let's look at part B. With a 30-year plan, right, we are paying $822.89 per month for 360 months. So that's going to be a total of $296,240.40. Okay, so that's how much we would pay out of pocket over the course of 30 years. But if we were to use the other payment plan, which would only cost us 13 and a half years, so we would be paying more money per month. So we're paying $1,000 per month, but only for 162 months. So this would be considerably cheaper. This would be $162,000, approximately $162,000. And you can see that the difference in that is $134,240.40. Okay, so the difference is quite staggering. And this is just the money out of pocket, not with really any interest or anything. $134,240.40. So by paying, let's look at the numbers actually. Yeah, so the difference between 1,000 and 822 is about $178. So by paying an extra $178 per month, so we can dig that up somewhere every month, over the lifetime of the loan, we would be saving ourselves $134,240.40. So you can see like the power of compounding interest when you are borrowing over a long period of time, and the power of saving if you're able just to pay a little bit more every month out of pocket over the lifetime of a loan. It's a huge amount of savings. All right, so hopefully this gives you a sense of mortgage loans, car loans. It gives you a sense of how these numbers are calculated. As always, keep working hard and ask questions. Thank you for watching and have a wonderful day.